All right. Yeah, actually this year marks my 15th year of contributing to SARE, OpenSARE, and Kamailio. And actually RTPEngine is quite as old. I think it's the 11th or 12th years, so not really new. The thing is that actually it started off as a media relay. You know, we had RTP proxy back then. We still have it with some pros and cons. What we did back then is actually focusing on a media relay, which is fast, which is really fast. Yeah. And over the years, we built on top of this a couple of more features. And in a chronological order, we actually started to create a WEBRTC bridge out of that. I think it was around 2011, 2012 when WEBRTC was starting, where there were people in Kamailio starting to implement SIP over WebSocket. Then crypto became a necessity in WEBRTC, so it was still Estes. Then we had DTLS. So we actually started to incorporate these kind of things to actually support WEBRTC calls over Kamailio. And then in around, I don't know, I think it was 2017, we started to explore even more, let's say, complex use cases because we had requests in Sipwise to create, call recording on a, let's say, carrier-grade level in terms of scaling. And adding additional, application servers doing this just makes, the call routing more complicated. It makes the troubleshooting more complicated. So we were thinking, we already have the media plane under control, so why not just hook our functionality in there? And this is why RTPEngine got actually bigger and bigger in terms of functionality. What we did last year, I'm not sure how many people of you are aware of that, we added media transcoding into RTPEngine. So what you can actually do is you can basically on the fly, while routing a call via Kamailio, transcode your media from G711 to Opus or any other codecs that we support. And just this year, we started to implement or actually deployed media player functionality. So you now can also inject media files and play arbitrary files. Again, removing the necessity to put, third-party applications into the SIP routing, like, I don't know, free switch, asterisk, SAMs, whatever, just for, tiny things like playing prepaid notifications or stuff like that. And I will go into detail, right, a little bit into detail, showing some examples of how to do these kind of things and how they actually work. So let's start off with the media relay. This is probably what most of you guys actually are using and what you are implicitly using if you use any of the features on top of that. The media relay functionality of RTPEngine is basically a kernel-based forwarding engine. It's not necessarily using the kernel, but it does by default. The thing is that there are more and more deployments using containers nowadays where it's sometimes difficult to load kernel modules. So there is an automatic fallback to user space forwarding with the trade-offs of higher latency and lower performance, of course. But in the end, it's really a kernel-based forwarder with a user space daemon interacting with an application like Kamailio and mostly Kamailio. It does network bridging, so you can do IP version 4 to IP version 6 bridging. You can bridge between two IPv4 networks. You can use DNAT stuff for AWS deployments where you are within a private network and need to advertise a public network. And the thing is that since it's really fast, it needs or it can relay a lot of media streams. And typically let's say one audio call uses 4 ports on RTPEngine. And it's not unusual that you can do something like, I don't know, 20,000 cores per server if you have a proper network card in place and proper tunings. And 20,000 cores would end up with at least, 80,000 ports, where you actually run out of ports, right? So what we have is IP load balancing, automatic IP load balancing. You can actually configure multiple IP addresses on an interface, and then RTPEngine starts picking random IPs and starting to pick ports from these IPs in order to actually utilize the ports available there. Because per IP, you have essentially like 64,000 ports available, right? And one of the things that, not recently, but I think a year or 2 or 3 years ago, we made it open source as well, is state synchronization with Redis, which is pretty interesting for, again, carrier-grade deployments where RTPEngine, when it learns about new cores and sets up forwarding rules, it syncs the state to a Redis database, either by just writing to it or also by using PubSub. And then you can have a standby RTPEngine there. So if you fail over, RTPEngine starts, loads the states from the Redis database, and reestablishes all the forwarding rules, right? And that means that you can essentially do failovers without any interruptions. It's like, I don't know, a couple of milliseconds. You sometimes hear a click maybe, but in the end, you really can fail over from one machine to the other and still have all the RTP streams continue to run. The way it works, as we said, is, okay, you have a Kamailio instance, but actually it could be anything. It could be Asterisk, it could be SAMS, it could be even a Node.js application. I think Brave Guy really implemented a module for that. So you have the control plane in SIP, right? So you negotiate your STP. And what you do is when you get an invite, typically, you push this information down to RTPEngine, telling it, okay, this is the STP, now do something with it, right? In the normal use cases, okay, set up a call, like set up the media relays. RTPEngine takes the whole STP, modifies it, and puts back the modified STP back there. This is actually compared to what RTP proxy was doing, like just rewriting IPs and ports. We actually replaced the complete STP body and write it back for various reasons we're going to hear in a second. And using this information, RTPEngine is setting up the ports on a user space. It waits for RTP packets. It starts learning NAT characteristics, like, in STP, the information could be different from what actually comes into the network or from the network. And once it has all the, let's say, the call X established, then it starts pushing it down to the kernel and basically relieves the user space from the forwarding work. And then you have a lot less of context switching and a lot better performance on the kernel level. The way these things interact with is you have an RTPEngine Kamailio module, basically drop-in replacement for RTP proxy. This RTPEngine module in Kamailio communicates via some particular protocol. It's a B encode protocol, something like JSON, but more lightweight. It communicates with the RTPEngine user space daemon, and the daemon basically controls an XD-RTPEngine kernel module. And the kernel module does the forwarding. And in the most easy case, what you do is you just call RTPEngine manage, and that's it, right? So this is what you do when you get an invite. You, of course, check, okay, do you have STP, and so on, and do you really want to relay the media? And if you want, then just call this. There are a couple of variations how you can start RTPEngine. As I said, you can use an interface definition. You can actually call or start it with an interface name instead of the IP, and then it will be call of the IP addresses bound to this interface. You can define more interfaces than one. Like in that case, it would be X, but you can also say, okay, I have an interface int and an interface X. And then in the RTPEngine manage, you can give it parameters saying, start bridging between the internal and the external network, or, you can have multiple networks and then decide, okay, I really need to bridge particular networks for, I don't know, peering calls, and then selectively choose the correct interface to route the calls to. Next thing, WEBRTC bridge. So what it essentially is a mode where RTPEngine is converting STP profiles, right? Typically, a normal core would be just an RTP AVP profile, and you can instruct it to convert that to RTP SAVPF, for instance, right? So you use RTCP feedback, you use encryption. In that case, when it's pushed down to the kernel, it uses in-kernel DTLS SRTP crypto, so you really have a really small overhead on the crypto stuff. It's around, I don't know, 10% what we measured, so not really that dramatic. It supports ICE negotiation, so what you can do is you can say, okay, depending on the mode I want to operate, I can actually add RTPEngine as another ICE candidate, for instance. So if the two endpoints are able to establish a peer-to-peer connection, then RTPEngine will do nothing, right? But if they're not, then they can use RTPEngine as another candidate in order to establish the connection. But you can very well also force RTPEngine into the core, saying strip all of the ICE candidates out that the peers were providing and just put yourself in there, right? And the other thing is that it does RTCP multiplexing, right? The standard mode of what WebRTC actually does. RTPEngine is able then to communicate on the same port, RTP and RTCP. Basically, it works the same, yeah? So you have, again, Kamailio, you have RTPEngine. What you do here, you have typically on one side RTP, just a normal, VoIP call. And on the other side, you have, for instance, SIP over WebSocket with DTLS SRTP. And what RTPEngine does is as I said, it changes the profile, it adds or removes ICE candidates, it adds RTCP multiplexing options into the STP, mangling it in order for the two peers to communicate to each other. And the way it works is in the easiest use case, as we said before, you can use RTPEngine manage, and manage is basically a wrap around an offer and an answer and the request and the response. You can do it individually if you need to, set different parameters on the different directions. Like in that direction, we say you get in an invite from a SIP phone, for instance. And in that case, we know we are going to go to a WebRTC client, so we use RTP SAVPF on that side, and we force ICE. And that will actually instruct RTPEngine to add ICE candidates into the STP information. And on the way back, you will get, like from a browser, via SIP over WebSocket, for instance, a huge STP body, and RTPEngine will start cutting it down into an RTP AVP profile, and will remove everything ICE-related. Will also demultiplex the RTCP, and therefore, a normal SIP phone without any WebRTC support can actually communicate with that. And RTPEngine then sits in the middle, talking SRTP on one side, plain RTP on the other. You don't have to do anything with RTPEngine in particular here. It will just work out of the box. Next, and I was showing that like 2 years ago already, call recording. The thing is that we do the crypto stuff in RTPEngine, and what you can do is you can say, okay, I want to record a call once the call is being established, or while the call is being established. You can also say, I want to start recording only during the call, for instance, for regulatory requirements, saying, I'm as a call center agent, I'm now going to tell you a credit card number or whatever, so I need to pause recording. You can use event routes for that and actually start and stop the recording part. And what RTPEngine does here is it actually forks packets that it receives on both sides into the proc file system using the kernel module, and it forks them in plain. So even though you get, you have, for instance, on one hand, an encrypted communication, you can actually still record it in plain if RTPEngine is instructed in the middle to encrypt and decrypt the two legs. The reason why it's being forked to proc is that if no consuming application is sitting on top reading it, it won't run the file system full. So this is one of the things that we have heard yesterday, that you could actually start producing like big amounts of RTP information, and if the recording daemon is not able to pick it up, then you would really flood your file system, for instance. And in that case, that's just a small buffer, and you can read, for instance, the proc file system, particular paths there in real time, and you will get the packets as they arrive on the network. And if you don't pick them up, they're going to be discarded. There sits an RTP engine recording daemon on top of that, listening, using kind of iNotify for some meta information, and then starting to read the packets as they come. It will convert them to PCM, and I will store it to WAV or MP3, for instance, on an NFS file system. And what it also does is, of course, it stores some meta information in MySQL because you really want to know first where did RTPEngine store the call, and also which numbers were involved or some user IDs, so that you later can actually identify the actual recording. And the way that works is, as I said, RTPEngine in that case, if you instruct it to record it, it writes meta information onto the file system, so in var spool recordings by default, and you can, for instance, listen via iNotify for changes in this directory, and every time you get a new file, you open it up, you read it, and then you will find the path of the actual media where it's being exposed, and then you can start reading it there, and you can read the two different streams individually from those, and the recording daemon on top actually starts reading that and starts, as I said, transcoding it into PCM. It stores the two streams individually, and it also stores a mixed stream together onto the file system, so essentially you have 3 streams. And it then stores it into wherever output directory you have, plus some meta information, as I said, in MySQL. All right, the way it works, pretty simple. You just instruct it to record the call, and then you give it a list of metadata that you actually want to store in MySQL, right? So in that case, we say we want to have a variable or a tag in the database called your UID, so a unique user ID that you can identify your A party and your P party with. And then wherever you get this A and P identifier, you just put it in as variables, for instance. RTPEngine needs to be instructed when you start it to prepare for it. There are 2 things that you need to do. There's an RTPEngine process, of course, but there's also an RTPEngine recording process you also need to start on top of that in order to pick up the calls. They are separated so that, first of all, RTPEngine stays simple and simple in a way of rather lightweight. And also if something happens with the recording and, for instance, the daemon crashes, that you don't bring down your whole system, right? So there is a recording method called proc. There are actually 2 of them. One is pcap, so you can also do RTPEngine recording to pcap files. In that case, we are using proc just to expose it, and you just tell it, okay, where are you going to store your meta information? In that case, it would be var spool RTPEngine. And that's it. I mean, you can, as I said, you can start and stop the calls during, or start and stop the recording. So check the documentation, read me on the protocol, what you actually need to do in order to do this. But that's, let's say, the basics for it. One of the more interesting things nowadays, media transcoding. So lots of carriers we know actually deploy SBCs in the network in order to do just the transcoding. Whereas you really don't need it if you already anchor the media path and you already process that. And this was the reason why we implemented transcoding. We already needed it in one way or the other for the recording anyways, right? Because we were receiving, let's say, G711 or Opus or whatever kind of media on the wire. And when you want to store that as MP3 files, you need to transcode it to PCM in any case, right? So that there was just a natural step to say, okay, if you already have it in PCM, then you can very well transcode it to another or encode it to another codec and send it off the wire again. And the way it works basically is that we utilize FFmpeg. There's just one drawback. It doesn't use kernel mode for that. So if you do transcoding, it happens in user space because there is no FFmpeg kernel implementation, unfortunately. There's a whole list of codecs it supports. So you just start RTPEngine -- codecs to see what you actually get. So depending on how you compile it, you get a more or less extensive list. There's one extension, G729, which is not part of FFmpeg. So this is actually being implemented via a different library. Yeah, there are actually 2 modes of that. One is a last resort mode, where you can tell RTPEngine to propose transcoding for a couple of codecs, and RTPEngine will add it to the offer sent to the P party. But if you get a response back, and if RTPEngine is able to match up 2 codecs that the 2 phones are, let's say, natively supporting, it will not do any transcoding. So actually, it's to save as much as possible resources on your service. basically being there just in order to be able to establish the call if really necessary, and then it's going to engage transcoding. But there's also a forced mode. For instance, if you say you have, let's say, a mobile WebRTC client, and you really, really want to use Opus narrowband, for instance, on the mobile network, and on the other side you want to use G711, you can actually instruct the RTPEngine to enforce Opus transcoding on one side, stripping off all the rest, and then just propose G711 on the other side, for instance. Again, not much difference. You just have G711 in that example on one hand. You want to do Opus on the other hand. So what RTPEngine does is it filters out all the unwanted codecs if you instruct it so, and adds the additional ones you want to do. In that case, we want to say, okay, we really want to enforce a call being Opus on one hand. So no matter what comes from the A side, we're going to mask all of the codecs, which means RTPEngine is going to hide them. And we say transcode Opus on the second side, so it will only propose Opus to the P side, and then it's going to have a negotiation between Opus and G711. You don't have to tell RTPEngine anything in particular for that, so it's going to just work. And basically the last big thing, media player, which has been just recently added, which actually allows you to inject arbitrary audio into media streams individually. So this would be to, I don't know, implement call whisper, implement, as I said, prepaid warning pings, announcements. Actually, there are regulatory issues, and this is why we implemented it. In some countries, when you start recording, you need to actually tell the calling or call party that the recording takes place. And not always the call center agent tells this to the customer, so you can actually automate these kind of things. And it supports playing it from local files or loading it as blobs from MySQL. This is a bit different in a way that you have an established call, and then via some means, you can, during a call, start playing the media. So what you have is you need to have actually a call ID of an existing call, and you need to have a from tag or a to tag in order to identify which direction, like which stream you want to inject it to. And you need to have an ID or a database ID. Sorry, a file or a database ID. And what you get back is basically a calculated duration if RTPEngine is able to estimate it. So you will get back, okay, this file you got me is going to take like 30 seconds, and you can react on that in the response. In our case, what you can do in this example is you can use RTPEngine an event route for XHTP, so you can send it a curl request if you want, or an API request. You will do some sanity checks, of course. And then what you tell RTPEngine is you say play media. You give it the call ID you got from your HTTP request, a from tag, like the direction, and the file. Yeah. So usually, if you wonder, okay, how do I actually get my call ID and my from tag? There are different means, of course, in Kamailio. You can actually, when you set up the call, you can, I don't know, store this information in Redis. You can send off an HTTP request to a third-party application telling it, hey, there's a new call between these two numbers. The call ID is this, and the tags are that. And then you can, in this web application, for instance, react on that and implement this kind of stuff. And one last thing is, there are more things we did. They are, let's say, minor, but could be very useful. One of them is DTMF logging. So if you ever experience in your operational work that people, I don't know, interact with IVRs and they complain that it doesn't work, you can actually look into the log files and check whether DTMF has been detected. Usually it's RFC 28, whatever. So it doesn't detect in-band DTMF in that case. But what you can also do is you can actually start blocking media and DTMF individually. In a similar way as you do with the play media. So you can instruct RTPEngine to say, again with the call ID and the from tag, to say, you know what, for the duration of this, I'm going to block forwarding of the stream from A to RTPEngine. And also block, for instance, DTMF traffic from this peer for various reasons you might have, like muting persons. The other thing is stream forwarding to third parties via TLS. This is pretty interesting because you can actually instruct RTPEngine to say, aside from forwarding all your traffic between the legs, you can also fork it and send it off, for instance, to a speech recognition engine. So it's, at the moment, it's really just a plain TLS connection, and then it sends the PCM packets over there. So there's no protocol like MSRP or something implemented, although we were looking or are looking into that. For now, it's really a matter of saying, okay, I want to start the forwarding to a particular third party, and then you can analyze, like, I don't know, the mood of a caller or doing, as I said, speech recognition. And what is pretty interesting is that it also supports MOS reporting. So actually you can, when the call ends, read AVPs. There are a couple of PVs actually that are populated. You can actually read the values that RTPEngine takes from the RTCP feedback and write it, for instance, along with your CDRs to your cores, so that after the call, if somebody comes and says, that was really bad quality, you can say, okay, well, the MOS value was, I don't know, 2 or something. You're like, okay. But if it was quite good, then you're like, you can actually estimate quality of peers, quality of connections, and I can take measures out of that saying, I don't know, I see a degradation of a particular peer, so I want to reroute my PSTN calls to somebody else for the time being. Yeah. All right, that's it. Thank you very much.
Thank you. Okay. So a few questions was first, then Sebastian second, and okay, only 3 guys because Andreas is here, he has more guys around, but we need to get in time for lunch, so.
Thank you for your report. It's very interesting. I have some question about media playing. You show that we can manage playing via XHTTP request event router. And does we have some can we request Kamailio for state of media streams? Can we request, does we have stream, and if we have stream in inbound and outbound, does RTPEngine mix or it replace media streams?
Like you mean conditionally, saying if there is no audio on one side, play an apology, or I don't know, what would be the use case?
Use case next. We have a problem with media streams, and we want to play some erroneous message to our user, but we must to know that we don't have a stream there.
Actually, there is an interface in RTPEngine. There's even a CLI tool where you can query particular metrics from a call if you have the call ID. So you can ask in real time or read the proc file system again. RTPEngine from a third-party application for a particular call, asking it, okay, how is the media, how many packets have been relayed, what is the bandwidth, and if you find some some strange things with that, you can actually start doing this and announce something to the parties, for instance. Yeah.
Okay, thank you.
Hi, I actually played around with the transcoding last week and got it to work successfully, and it took me a while to eliminate the PCMA, PCMU from the SDP. But did you do testing how many calls one machine can transcode?
We did some testing. I think it was some Xeon Silver machine with, I think it was like 8 cores, and it did around 800 or 900 cores in that area. It really depends very much on the codecs, of course, but this is the range where you get. So you get a degradation of at least a factor of 10 minimum, if you do this.
Okay, Federico.
Okay, actually I have 2 questions. One is about those new play media command. Will there be an RPC version for those commands?
Not really. I mean, there are different approaches how you could do it. The thing is, you don't have to use Kamailio. You can use Kamailio for that. Like saying, for instance, you do an event route. There is no RPC command particularly for that. But what you could also do is you could inject your command via different means and not directly via Kamailio.
Yeah,
you could actually write an RTPEngine client telling it directly to do it. Yeah.
Okay, and the second one
Last
is
one.
about it's about transcoding.
Yeah.
Is there any jitter buffer for?
Yes. Yeah,
And
there
is
is a
it
jitter.
configurable?
It's static. No, it's static for the sake of adapting to different packetization times. Yeah. Adaptive jitter buffer is something on the list, has been asked a lot for. We didn't get any funding for it yet, but there is a lot of, let's say, interest in that. I don't know, maybe we can do it this year. Let's see.
Thank you.
Okay, thank you. We can't take more questions. Sorry, but catch Andreas. Next will be the lunch. And
I will be around anyways for the next 2 days.